We've made a lot of progress defining free energies, and we've even seen that they give us back the intensive quantities that we've been studying so far. But if that's all that they're important for, then that might not justify their use. We already have the intensive quantities and we've been working with them for most of the course. Today's video is about telling you that free energies give us a lot more than that. In fact, they're so fundamental that I might say that this is going to give us a whole new look at classical thermodynamics. So let's launch right into it. And I want to do that by talking about something that we'll need as we continue on in the video, which is what is the free energy of a reservoir? Let's look in particular at a thermal reservoir's Helmholtz free energy. So the Helmholtz free energy, I'll remind you, is defined, usually called F, and defined by U minus Ts. Now recall that for a thermal reservoir, we have that S is proportional to U, and then since partial S partial U is 1 over T, we find that S must be U over T. Good. Now let's stick S back into F. So we'll get from these two together that F is equal to U minus T times U over T. But check it out. This T in the numerator cancels this T in the denominator, and we simply get U minus U. So that means that the free energy here is specifically 0. And this will apply for any for the Helmholtz free energy of any thermal reservoir. Good. Okay, so now let's see if this applies for all reservoirs. Is this really only something that applies to the Helmholtz free energy? And the answer is not quite. Anytime we're doing a thermal join, or sorry, we're talking about a thermal reservoir that is also another kind of reservoir, it also applies. The easiest example is a thermomechanical reservoir, and we'll see that this works for the Gibbs free energy. So just to remind you, the Gibbs free energy is given by G, which is equal to U minus Ts plus PV. Excellent. Now, I said that this works for a thermomechanical reservoir, in other words, one that is both a thermal and mechanical reservoir. Which implies that the entropy is proportional to U, or I should say linear in U, and also linear in V. So for the time being, let's say alpha U plus beta V. But now, since we've written things in internal energy work coordinates, we have a pretty easy time figuring this out. Because partial S partial U, as we've already said, is 1 over T, which gives us the value of alpha. And partial S partial V, since we're in internal energy work coordinates, is P over T, which gives us the value of beta. So this implies that S is equal to U plus PV all over T. Now, let's do the following. We'll multiply T through on both sides. Then we'll move the Ts from the left-hand side here to the right-hand side. And that will give us U minus Ts plus PV is equal to 0. But then compare with the definition of the Gibbs free energy. This implies that G is equal to 0. Okay, so this gives us a sort of lemma that we'll need as we go on to our next discussion about the free energy as being a sort of governor of what happens in the system. Recall how things worked for an isolated set of systems. So remember our rule for joins. In a join, we moved to the point in the state space which maximized S under, or sorry, maybe I should say on constraint space kappa. Let's think about a thermal joint in specific. In this case, we maximize S, while fixing total energy U total. With all of this in mind, I want to look at a specific example case in which we actually are going to do a join between three simple systems. The first two are just ordinary gas systems with coordinates u, v, and n. Now, I'm doing this just for simplicity's sake. We could use internal energy work coordinates for any system we wanted. The third system will be a thermal reservoir. Awesome. And now let's do a thermal join on the system. So before we start on that, actually, just for clarity, let's make sure that we write down that S3 is equal to U3 over T, and I'll call it TR rather than T3, just to make sure that we know that this is the temperature of the reservoir. Okay, I also want to remember that, that F3 is equal to 0. That will be important in a moment. Okay, let's press on. We know that what we need to do is maximize S while fixing U total, which is equal to U1 plus U2 plus U3. With all of that in mind, let's consider F total. Now, the free energies, much like the internal energies, are nice in that their sum is just the sum of the individual free energies. So F is going to be equal to F1 plus F2 plus F3. But I want to remember that F3 is equal to 0, which we have here. So this is also just equal to F1 plus F2. So that's going to be one way that we reduce F. Now let me switch colors and we'll think about a different way that we could reduce F. And that is to switch each of F1, F2, and F3 out for its expression in terms of U, T, and S. So this will be U1 minus T1 S1 plus U2 minus T2 S2 plus U3 minus T3 S3. Now let's start reducing this. Now let's start reducing this. So a few things that we can consider. U1 plus U2 plus U3 here all add up to U total. Moreover, at the final point, the point where these end up, T1, T2, and T3 must all equal TR, since all of these systems are in contact with a thermal reservoir at temperature TR. So all of these become TR. So now we can significantly reduce this equation. We see that this is equal to U total minus TR S1 plus S2 plus S3, but that's just S total. So I'll just say S. But now look at this. U total is a constant on our constraint subspace kappa. TR is a constant on the, or I should say TR is whatever the temperature of the reservoir is at the final point. So we find the following, that if we have these three systems in contact and one of them is the thermal reservoir, then maximizing S is precisely the same as minimizing F. So max F, sorry. So min F, if and only if max S, here we'll have subject to the constraint, the reservoir is at temperature TR, and here we'll have subject to the constraint that the energies are constant, or the sum of the energies is constant. Good. Now there's one more thing to notice here, which is that when I think about minimizing F in this way, I can think about minimizing F1 plus F2 plus F3, but since F3 is 0, this is actually exactly the same as just minimizing F1 plus F2. And this gets us to a whole new way of thinking about classical thermodynamics when we are in contact with the reservoir. Let me erase the board and I'll talk a little bit more about what I mean. Okay, I've resurrected a table that we saw in a much earlier video. And in that table, we presented the different kinds of reservoirs and the different kinds of work operations that we had while we had the system connected to that reservoir. Just to be really clear, the setup that we have here is this. We have one reservoir of the type given in the left-hand column, and then we have potentially many other simple systems. But all of those simple systems are always connected to the reservoir. So they'll always have whatever the reservoir's intensive variable is fixed at a fixed value. Good. We learned basically at the beginning of the course that if we were not in contact with any reservoir, then the only work operation that we could do was an adiabatic work operation. And the rule for joining two systems was that they always maximized S, their total entropy. For a thermal reservoir, we've already found that the correct work operation is an isothermal work operation. But now we can also fill in what the rule is for joins. They'll always minimize their Helmholtz free energy. And just to talk for a second about what the constraints are, now the constraint that the total energy is fixed is replaced by the constraint that the temperature of all of the simple systems is always the temperature of the reservoir. If we think about a mechanical reservoir, then the work operation that we found makes sense in that case is an isobaric work operation. And we can now say that the join rule is that we minimize H, the enthalpy. And here we'll be subject to the constraint that the pressure of all of the systems is always the same as that of the mechanical reservoir. And we could fill this out for any kind of reservoir that we wanted. The work operation would always be an equal PI work operation, and the join rule would always be that we maximize the free energy that has Legendre conjugated the correct work variable. This really motivates us to think about classical thermodynamics in a slightly different way in terms of what control operations we have available to us. And that's because we often will find that we're not in connection with no reservoir. In other words, we don't have isolated systems, but rather we're dealing with systems in a laboratory setting or an industrial setting, which are connected to their environments. So we imagine, for instance, a benchtop experiment that's being done at atmospheric pressure, or an experiment that we're doing in a refrigerator that's being done at whatever temperature we've set the refrigerator to keep. In those cases, it makes sense not to use the sort of regular control operations that we defined for isolated systems, but rather the systems that we've defined for when we're in contact with a reservoir. We learned from the last board that we can effectively ignore the reservoir except insofar as it changes the work operations and the join rules here. And so that gives us a lot of flexibility to deal with different kinds of conditions. In particular, it allows us to deal with doing experiments at constant temperature and pressure, which is a thing that I'm sure people are very, very familiar with. Before we end this video, I do want to talk about one other way of thinking of the free energies. This is maybe a bit more esoteric, but I really like it, and it's sort of drawing on examples from Introduction to Thermal Physics by Schroeder, which is a very famous undergraduate textbook. The idea is that we want to think about creating systems from the void. We imagine that we have some kind of magic that allows us to create systems, but doesn't allow us to create systems without energy. So we still have to somehow put energy into the system to create it. All right. That said, we are allowed to use energy that we find elsewhere in order to create the systems, and we have to account for extra things we may need to do in order to create the system where we put it spatially. So let's first think about the case where we're creating a system truly in the void, in a vacuum where there's no sort of connection to anything else. In that case, imagine that our system is a box of gas. The energy that we need to provide is simply U, the energy of that box of gas. Let's think of a second example. In this one, we're going to create a box of gas once again, and we'll do it in an environment with negligible pressure, but with some temperature. The reason that the temperature is important is that whatever spatial region we're now going to be filling with this box of gas has some thermal energy in it already. And it turns out that if we think of this system as being a reservoir, which it is by our assumption, then we know what that thermal energy is by the simple relationship between the entropy and internal energy of a reservoir. In particular, we now have to provide the internal energy U except for the energy that we can get from the reservoir itself, which we find to be Ts. So we get Ts just without having to make it. The last example is one in which we have a box of gas that we'd like to create, but in this case, this box of gas is in a thicker atmosphere where we do have to worry about the fact that there were already atoms here that we now need to move out of the way. If we think about the region here as being a sort of box of gas of its own before we put this new box of gas here, then we need to take that box of gas, which is at whatever the reservoir's pressure P is, and move it out of the way. Now, if this new system has volume V, this is like compressing a piston because the box of gas of the old reservoir needs to be pushed out of the way and is at pressure P. So we need to push with at least pressure P, and we need to push it out of the volume V, which means we need to provide work P times V. The upshot here is that we need to provide the energy U to create the internal energy of this box of gas, but we also need to provide the work PV in order to move the old gas out of the way. But if we look at what we have here, in the first case, we have a box of gas in an isolated environment, and we needed to provide U. In the second case, we had a box of gas in a thermal reservoir, and we needed to provide F. And finally, in the third case, we had a box of gas in a pressureful environment. I'm not sure if that's clear, but seems clear enough to me. And we needed to provide its enthalpy, H. So this gives us a sense that the free energies are the energy that we need to create the system in the environment in which we are creating it. And so maybe gives us that kind of same sense that it allows us to deal with certain reservoir types without putting them into our set of simple systems directly. I do want to comment on one final thing before we go, though, and that's that the term free energy has really bothered me as I've put together this material. The reason is exactly given by this analogy. The free energy, or what we call the free energy, is actually precisely the not free energy. The free energy is, again, what we need to provide, what isn't provided to us by the environment. Now, I'm not sure what the reason is for this sort of linguistic confusion, but I do think it's very interesting. And I'd love to know if it's the result of some historical accident or something else. But that mystery aside, thank you so much for watching, and I'll see you in the next video.